Welcome to the course Business Analytics and Data Mining Modeling using R. So, in the previous few lectures we have been discussing classification and regression trees. So, we discussed different issues that we face while building classification models and the recursive partitioning step and the pruning. So, specifically we have been discussing pruning steps, and we talked about different scenarios and how the pruning can be performed and the problems that can be faced while pruning. So, in previous lecture we had talked about the pruning sequence. So, we will again focus a bit about this in this particular lecture. So, pruning sequence till now we have performed two ways of pruning. One was just for the illustration purpose, just for the demonstration purpose, where we followed the node numbering order, node numbering sequence to perform pruning. So, wherein the unique node numbers that are generally generated for a particular tree model that were used to perform pruning. So, as we talked about, this was just for the illustration purpose, and the tree that results from this particular pruning process looks a quite balanced tree because the node numbering sequence that is being followed. However, this is not the the optimal tree, that full that full grown tree that we talked about, and pruning it back to a level where it doesn't overfit the noise, or it doesn't overfit the data or fit to the noise. Therefore, we talked about creating a pruning sequence which is based on the complexity value. Creating a pruning sequence which is based on complexity value. We also talked about in this discussion that we have to follow the splitting order, right. So, if this is the root node, so first split predictor and value combination that we talked about has to be this. Then we have to see which one of the right or left child is going to provide further impurity, going to give us further impurity reduction, and therefore we have to the split is going to be performed on that particular node. And then for next split again we will have to compare within the remaining nodes, right. So, in this fashion the splitting order would be created, and we talked about that we will get a pruning sequence which would be the desired sequence that we want, right. Now, in this particular lecture what we are going to discuss is combining these two approaches, because we would still face some issues while we do our pruning based on the complexity parameter values. We will understand this. As we have understood in previous lecture that the complexity values, right, CP values. So, for once the exercise in R that we had actually did in previous lecture, we had sorted our decision nodes and the split based on the complexity values. So, we had a toss variable which was capturing the sequence of nodes as per the splitting order, right. So, let us say for example, this is highest value is 0.3, and there are some nodes here in this particular column. Then we have again something like this, then some value are in this fashion the values are going to be there, and based on this sorted complexity order we created our splitting sequence. Now, we will cover the problems that we might encounter. So, for many nodes this particular, as we go down the tree, many nodes will have the same complexity value. So, there might be many such decision nodes which will have same complexity value, and therefore, which particular node is to be pruned first is going to be the question mark, right. How do we decide which particular node should be pruned first? right. So, as the tree grows further, some nodes that we would see, they will carry same complexity value. Now, how do we decide our pruning, our pruning sequence here, right? So we have sorted. So this is the optimized pruning sequence, right? So for root node 1, this is the highest. So once the full grown tree is developed, so we start splitting from the least important split. So that means from here, right? So corresponding node which is having the least complexity value, that would be pruned first and will move in this fashion. However, when we come into these zones where the nodes are having the same complexity values, then what typically happens is in the prune.r part function that we have in R, that will actually prune the tree from the node which will give us the smallest tree. So for example, if these were the nodes, and this particular node also had, let's say this particular node also had the same value. So out of all these nodes which have the same complexity value, the prune.r function will prune from here. It will prune all the nodes. It will prune all the nodes from here, and will give us the tree with the smallest number of node. So smallest subtree would actually be written there using prune.r part function that we had used in previous few lectures. However, the method that we are following, we would like to follow this sequence, of course, but whenever we encounter these groups of node having same complexity values, we would like to prune the node with the higher node number. Let's say this is 22, 44, then let's say this is 45, 90, and then here we have 180, 181 in this fashion. So as per this particular sequence, and we would like to, as we go about pruning different nodes, we would like to prune those trees which have higher node number. So therefore, when 4 or 5 nodes are having same complexity values, we will like to prune with the we would like to prune the node which is having the highest node number. So probably this is the node being at the rightmost part of the tree and having the same complexity value for some of these regions, right. So that would be the node that we would like to prune first, and then will move further. So now in the exercise that we had performed, we will have to make certain changes in the code that we did in previous lecture. So let's reach to the same point and we'll discuss further. So let's first load these packages XLSX and then R part, and then R part dot plot. So let's load these packages. So once these packages are loaded, let's import the data set that we have been using in previous few lectures, promotional offers data set. So let it load, and then we'll look at the some code that we will have to change. I'm also going to correct a few minor problems in the code that we had used in previous lectures. So some minor corrections in the code, and also we would like to accommodate what we have just discussed, right. So if we again to come back to this point, earlier we did an exercise where node numbering sequence was followed, then we did an exercise where splitting sequence was followed, but splitting sequence also run into this problem. Now merging these two approaches, you would see that though we follow a splitting sequence for pruning, but for few groups having same values, we follow the node number sequence, right. So, the nodes with higher value, right, they would be pruned first. So, the code is to be changed for the same, and we will just see. So, data is loaded already here. So, let us perform some of these steps, grouping categories that we have been doing in previous lectures. So, let us create this pin code categories. So, now let us convert these variables to appropriate data types, variable types. Let us do partitioning as well. Now, everything is okay in this structure function. Promotional offer is factor, pin code is factor, 13 levels, online, education, everything appropriately mentioned here. Now, let us do the partitioning. So, we will just so now this was the model that we have been using, mod 1. So, this is done. Now, let us move forward to the place where we were performing pruning. So, here we were performing pruning. So, this time in this particular run we have total number of nodes 87, total number of decision nodes 43, and total number of terminal nodes 44. One thing by now you must have observed that every time we run this model, the number of nodes that have been part of the tree, and then within that number of nodes in the decision tree, and also number of terminal nodes. So, the total number of nodes and also the number of decision nodes and number of terminal nodes have been changing every time we run the model, right. Though we have a good amount of observations. So, we have 2500 observation in training partition, even though this has been changing. So, we will discuss this particular aspect, that this is mainly because the classification and regression tree model, they are quite sensitive to sample changes in sample. So, because of this, every time when we construct a tree, we get slightly different result, because every time when we randomly draw the observations, they are going to change, and therefore tree is also changing. So, the model as such is sensitive to sample changes. So, we will discuss this further. So, now let us go back to the point we were trying to perform here, merging those two approaches, splitting sequence and node number, as we have just discussed. So, let us first create this toss argument, which is the which will actually contain the number of nodes which we would like to prune, which will be used to determine our pruning sequence. So, as we did in previous lecture, let us create this data frame. So, this has toss1, this particular variable, and the variable used for splitting, and then complexity values for the corresponding variables. So, once this data frame is created, you can see 87 nodes in all the nodes of the tree. Let us remove the terminal nodes using this particular code. So, you would see terminal nodes are removed now. Now, let us look at this particular code. So, we wanted to create nested sequence of splits based on complex tree. Now, this was the now commented out line, this was the one that we used in previous lecture. Now, improvement on this is that now this particular data frame is being ordered or being sorted first with complexity values and then with node numbers, right. You would also see a minus sign before this particular variable for node number. This is because we want to sort our data in the decreasing order for complexity values, but once the for the group for the group of nodes having the same complexity values, we would like to order them in increasing sequence, right. So, first node with lower node number, then followed by nodes with higher node number. So, that is why minus sign is there. So, you can look for more to understand more about order function. You can look at help section, and there you will get examples also how we can manage this. So, this sorting is actually by the sorting that we are trying to perform here is actually by multiple columns, right. So, let us sort this data. So, this is done. Now let us also change the row numbers. So you can see 43 decision nodes, and now they have been sorted. If you want, we can confirm this through one or two examples. So let us look at the unsorted let us look at the unsorted list, and this one, the last one, you would see that this one is okay. The node numbers are also in the desired sequence. This is also okay. Now let us move further to find out an example. This is also okay. This group, you would see that the complexity values are same for these many nodes, and the node numbering is also in the desired order, but there might be situations where they might not be in that increasing order. Node numbers might not be in increasing order for the group. So let us see this one, this particular value, this is quite large group, but this is also seems to be in the desired order. This seems to be in the desired order as well. Now let us look at this particular. This is also in the desired order. So probably in this particular run that we have done, everything was well in place. However, if we run again, probably we might not get this particular data frame in the sorted order, node numbering orders. Now once we run this particular code, we will get this in the so it will be decreasing complexity values, and within this list, within this particular list, the rows having the same complexity values, they would be in increasing node number orders now after having run this particular code. So here we won't have any problem if that was there in the first place. Now once this is done, now with this we would be able to use this particular pruning sequence to perform pruning, right. So now the pruning would happen with the least important splits. That means the nodes having the least complexity values, and within the nodes which are having the same within the group of nodes having the same complexity values, nodes with higher node number would be pruned first, right. So with this we will repeat our exercise what we did in previous lecture as well. Few minor corrections have been done. For example, earlier these different models for different number of decision trees that we were building, now we are going to record them in the list format so that we are able to easily access them. So earlier this part of the code was not functioning properly, so we have made certain minor changes in the code to be able to record this. Now these particular variables, these three variables, mod1 split v, mod1 s train v, and mod1 s valid v, they have been initialized as list, and therefore in the loop itself will have more of a chance to be able to record all these models. So the code for within this loop is same as we saw in the previous lecture. So let us run this. We will have to since we are calling this function importance, so we will have to load it once this is done. So let us move forward. Let us come back to this same point. So let us run this again. Now once the importance function is loaded into memory, so this will done. So you would see that now let us look at the environment section. Now you would see that a mod1 split v, it is a large list of having 43 elements. That means all the models, all the successive models that have been built in this particular loop, all of them have been recorded. The same is true for mod1 s train, the scoring, and mod1 s valid, the scoring for validation partition for all the models. So once this is done, so you would also see one slight change is that now this particular toss3 is running from I to length of toss2. That means the number of models that we are running is from 0 decision nodes to 43 decision nodes. So last one within this loop would have 42 decision nodes. So this is appropriately mentioned here. 0, this is minor correction, earlier it was 1 to this particular value. Now this is from 0 decision nodes to 1 less than the total number of decision nodes. So this data frame is very much similar to what we created in the last lecture. Let's create this. Now the last node, the model with all the decision nodes is the full grown, nothing but full grown tree model. So we'll add a row for full grown tree model in this particular data frame. So you can see that here the last row is nothing but mod 1, that is full grown tree model. So we are adding the relevant details here, the number of nodes, then performance on training partition, then performance on validation partition. So we'll have to first score these two variables. So we'll go back to the part here and let's score these two partitions using full grown model. And then we'll come back and create that row again. So let's create this value. Now we'll have the data frame. So you can see in this particular output that 0 decision nodes, number of decision nodes 0 to number of decision node 43. So 43 one is the full grown tree model, and therefore in today's output, in this lecture's output, you would see that the training error in training partition is 0. That means tree completely fits the data, right? That leads to overfitting. And now we have the corresponding numbers for when we don't have any decision nodes 0. So that is just the root node, that is what we have. So those numbers are also here. Now this data frame now can be used to find out the best tree, best pruned tree and minimum tree, which we will do in a while. So now since we have made some changes and now we are able to access all the models that we have developed in this loop for different number of decision nodes. Now this one is the last model, the model having one less node than the full grown tree. So this is in mod 1 split. We can also access this using the list notation. So this is the full model. If you want, we can. You can see this is the full model. So you this is the last model with just one pruning of one node, right? And if you want to compare this with the original model, that can also be done. So here we can create the tree diagram for the full grown tree model. From this you would sometimes it might be possible for us to visually find out which particular node has been removed, so least important node. So the same thing we can also cross check using the particular data frame that we had created, DFP2, right. So this one also can be used. So this particular node should be spending from this pruning sequence. So let's look at this particular data frame. This is tree model for full grown tree. So the last node should be spending, right. So this is one terminal node. This seems to be one node, right? One decision node related to spending. Now let's look at whether this was the same one in the last tree in the loop, the last model in the loop. So it will take some time to load here. Node number is 163. So probably this one should be. So there is one more spending node here. So this could be 163, and we will have to see it. We have to compare this with the full tree model. So to visualize which particular node has been deleted. So I think 163, road number 160, this could be the one. So we can see here that spending 2 point, it's visible there. 3.6, this one is also present there. So this we can, so right now we will not look to spot this particular node. So one node, there is one less node. So let us execute these 3 field lines. So you would see that total 85 nodes are there, 42 decision nodes and 43 terminal nodes in the last tree, which removed which pruned just one least important node. And if we look at the full grown tree, number of decision node in the full grown tree, so there, that is 43. So one node has been removed. However, another way to spot this is using this particular output mod 1 here. You can see here, but however this is in the node numbering sequence. So if we look at the earlier output that we had saw, so where we expected that the node that has been removed is the node number 163. Now, if we look at that particular node here in the full grown tree example, that model results, right. So 163 is somewhere here. So this is where 163 is. Now the same thing we will look to find out in the last output that we had in the loop. So now instead of looking this point, we will look for the different models that we have stored here. So we can see that mod split 1v. Now with it using the double bracket notation, we can access the first tree after first snip. So this we can again create. So you would see this is just nothing but root node, and you can also look at that there is just one node and no decision node and just one terminal node. So this is what happens in the first after first snip. Similarly, we can access other nodes, right. Now let's plot let's create this particular plot between number of splits and error rate. So error rate going on the y axis. Let's look at the range. So this is between 0 to 10, around 10. So let's create this plot, also at the validation. Now you would see the plot is quite similar to what we have been creating in previous lectures as well. So you can see that training partition, the error keeps decreasing till it reaches 0, and for the validation partition the error keeps decreasing and reaches a minimum point somewhere here, and then after that it starts increasing. So this minima point is the one where we would like to prune the tree. Up to that point we would like to prune the tree. So let's find out this particular point. So as we have done in previous lecture, so this using this particular code and the data frame that we have created, we can find out. This is the tree, this is the error, and the corresponding number of nodes is 6. If you are interested to look at the data frame once again, we can do that. So you can see 0.017 and number of nodes 6. So this is the point. This is the point where minimum error is there, and the minimum error value is 0.0173. Number of decision nodes are 6. Now this being the minimum error tree, let's try and find out the best pruned tree. So let's compute the standard error for the error rate on validation partition. Now let's compute this particular value so that we are able to find out the best pruned tree. Now, this code we have already discussed. So, best pruned tree also comes out to be, in this particular case, best pruned tree also comes out to be the same as minimum error tree. So, we look at the table, we will get a better idea that the value that particular row that we are looking for should have the error, validation error less than this particular value 0.0198. If we go back to the table at 6 decision nodes row and 0.0198, we go up and we do not see any value. So, therefore, the minimum error tree itself becomes the best pruned tree, because within one standard deviation there is no other options available. So, once this is done, we can create the toss3 argument and create our best pruned tree diagram. So, if you look at best pruned diagram now, so this is the best pruned tree that we have, right. So, we have income, education, family size and spending. So, these are the important variables that we can see in best pruned tree, right. So, income being the most important, coming at the top of the tree and again reoccurring, and then spending is also there. Education also seems to contributing to this tree model, coming at the top of the tree here, second level, and then here as well, right. So, these are some of the important trees that we can see. Now, the same process we can look at using the r-parse prune. So, that is so for that we will have to specify x value as 10, that is the default value. So, let us go through one more time like we did in previous lecture. So, let us create this model, let us look at the CP table, and from here we will try and find out the row for which x error is minimum. So, this x error is similar to what we have done for validation partition, that error that we had computed. So, this is the value, lowest x error value, and the corresponding CP value also you can see. So, let us record this, and once this is done, we can also plot, we can also create this particular plot. Plot CP function. So, it will actually give us a graphic for CP versus this relative error, x value relative error, and size of tree is also you can see here, and the top axis and the bottom axis we have CP value. So, generally it is considered that first tree which is below this dotted line, right, in the left part of the plot, that is the best pruned tree, right. So, many points could be below this line, as you can see in this particular run there are very few, but you can see this particular range 9 to 22 and from 4 to 22 we can see that all these points, all these sub trees, they are below this particular reference label. So, generally best pruned tree minimum tree is around seems to be around this particular mark, right. Now, the typically best pruned tree is the first point after which comes below this line. So, this could be around after 4, this could be around 5, right. So, corresponding CP values then CP value can then be used to prune the tree to back to that level. So, this is a quite similar approach to what we have done, but this is based on complexity values, and we have already discussed some of the problems that we might encounter there. So, as per the process that we have adopted, sorting by complexity values and then further sorting by node numbers, that will give us probably the best models. So, we will stop here, and in the next lecture we will start our discussion on regression trees. Thank you.